Okay, all right. Yeah, so for the project, right? So most of the people in the class, the project ends up being using some historical data. Let's try to predict what happened in the future. That's for vast majority of people's project. And the other people's project, may not be exactly that type, but there are people doing, for example, appliance level data forecasting. There are people doing fault detection, right? Using some data, kind of predict some faults. Of those projects, the outcome is sort of clearly defined. Right? I don't think we have very nebulously defined project this time in this class. So mostly is I have some data, I want to take this data, I want to predict what will happen in the future. Right? That's how you do load forecasting. So the first step is to take a look at the data, try some examples, try some technique we have used, for example, linear regression, and see what comes out. Right? So you know the data you have, you know the target you want, do linear regression, and let's see how good your prediction is. Right? So if the prediction is good, congratulations, you're done. If the prediction is bad, then maybe that you don't have enough data. Maybe that your method is not powerful enough given the data you have. Then as next step is think about if your result is not so good, what do you do, right, for the next step? Right? Maybe we need to look for other data source, or maybe we need a method that's a little bit more sophisticated than just say linear regression. Okay, so the idea is, again, for most projects, the data is fairly clear, the target, what you want is very clear. Just give a try to see it works. And so again, if you've done that, right? So if you take your data and let's say you try to, so I think a number of people is doing something like either forecasting load or forecasting renewable generation using some data. So let's say you tried it and you figure out it doesn't work. That would be a good time to again communicate with me to say that, okay, this is my data, this is what I want to do, this is what I tried. It doesn't work. Well, the performance is very bad. What do I do? Is it because I don't have enough data, or is it I should use a more advanced technique? Right. So that's where you go in the next step. But the first thing is just say if this is the data, then let's try it. Right. We know the basic method. We have some data, and let's just see how well it does. Right. At least that gives you a baseline of what performance is. Other questions to add on that? Yeah, you gotta choose a topic, right? I think, yeah. Okay. So you have to come up with at least a broad thing you want to look at, right? So if you have no idea, then say I have no idea. That'll give a topic. I did receive a couple emails saying I have no idea what to do for the product. I made some suggestions, right? So that's a way that's perfectly fine, right? Nothing wrong with that, right? But what I don't want to do is to give a very standard set of data and give everybody the same problem. That's not too interesting because most of this project, what comes down to is working with the data that you find somewhere else, right? So again, if you have a project, even if your project is very, very standard, right? So the most standard project you can do in this class is you find some solar and wind data and say, I want to do a renewable forecast. So given the last hour or last day of data for wind, let me forecast what the next 24 hours wind data will be. That is about a standard project you can do. This is, this you can do this with regression, certainly. You're very clear what X is, you're very clear what Y is. All the numbers are real numbers. You have a clear loss, and taking what we learn works for that. Even in that case, you may think, oh, everything is easy, and I can do it, last week of the class, and just be done with it. Turns out what you have to do is you have to be careful how you parse and reading that data. The reason is, so how many, so for you guys, how many hours is in a year? How many hours is in a year? Most of this data is hourly data. How many hours in a year? Right, so 365 times 24, right? 8760, so this is a number you see a lot. And if you just use that, if you hard code that in, for a lot of data set you see that doesn't work. Anybody know why? You actually end up with weird issue that's hard to debug. Right? The reason is there is a leap year. It depends on how long you look. There's leap years in the data. And then you have this 24-hour offset. If you hard coding a number of hours in a year, you don't notice. Then that can actually screw up your prediction later on. So this can screw up your prediction. You may be training and looking at different sizes of the data set. And in any data you find, you may have data that are missing values. Especially for some of you, I have suggest, for example, data sets from Pecan Street. Those are data, real sort of measurements from homes in Austin. There may be times when just a measurement device went offline. So you have sort of missing data that's not there. Again, if you're not careful, you reading zero when it's actually missing data, or if your algorithm is smart, it will say this is not a number, but then you have to sort of tweak your algorithm to go around that. So a lot of this project is actually reading data, working with this sort of realistic data, figuring out how do you line it up, how do you deal with missing numbers. If you have, for example, if you're doing wind forecasting, every turbine has a capacity limit, right? So your turbine has a capacity limit of 10 megawatts, your forecast cannot be 15 megawatts. That's physically impossible, even though your algorithm may tell you that. So a lot of comes down to this kind of exercise, making the data make sense, making alpha make sense. So that will take you some time just to try and look at the data. So none of these are, very hard in some sense to deal with, but just some work going to the data. So I don't want to give you a clean data set and have everybody do the same thing. Now again, today, now the tools are good enough. That'll be 5 lines of code and we're all done. But it's like your homework, right? It doesn't really take that many lines of code. You write your homework, you change a few numbers in the code, you press shift enter, then you're done, basically with that. Right, so here the exercise, a lot of it is can you work with realistic data? That's not perfectly clean. That has sort of, different idiosyncrasies with different data sets and have sort of real life features. Okay, so the first thing is take the data set you found or have suggested, just try the most basic algorithm, see if whatever you want to do works. For people in this class, the vast majority is forecasting. So take your data, do linear regression, forecast, see what comes out. See if that thing is at least within the ballpark of what you would expect. Or see at least you can read the data and line the data up, line up the X and Y, and see if that works. Okay, so that's a lot of part of what if you ever do a job in this, that's what your job is. It's reading, writing the data, cleaning the data, looking at things that whether things make sense or not. It's for the algorithm part, applying any of these techniques again is all basically single line command at this time. Okay. Right, so again, if you haven't got in touch with me for the project or you don't know what it is, just send an email saying, I don't know what I want to do. I'll find you a topic to do for the project. Okay. Right. But every time, if you wait a week to go, it's not the method that doesn't work. But your data is way too messy, you can't clean it enough. That's what causes most people issues. You have, numbers that doesn't exist, you have missing data, you have wrong data. That take some effort to figure out. No questions about the project? Any question about homework? Yeah, go. Mhm. Right, yeah. So order sort of how many previous number of data points you look at. So that's called the order of the model. So seven is you look back seven steps. Mhm. The next hour, that's right. Yeah. So forecasting algorithm. So let's actually have a quick sort of look at forecasting because many people are doing a sort of project on this. So forecasting, what do you do for forecasting? The most common type of forecasting is use historical data to forecast what happens next, right? Use historical data. So the way you think about this is you have some data x1, x2, x3, up to xt, and you want to know what happens for xt plus one. Okay, so this is your current time. Right? So x1 to xt, you have all this data. This data is available to you. Your goal is to know, okay, what happens next, right? Can I forecast what happens next? This is used every day. This could be load forecasting. Right? This could be load forecasting. It could be forecast given some historical load. You forecast what happens next. It could be, let's say, wind forecasting, solar. Right, so a lot of forecasting algorithm is I observe some sort of process, observe his history, can forecast what the next is. Okay? So in principle, you could use all the historical data you ever have, right? In principle, you observe all this data, you could use all of it to forecast what happens in the next one. We don't do that because that's way too complicated. Again, let's say I want to forecast a load for tomorrow. It doesn't make sense for me to use the whole past year of data, right? I don't want to use the entire historical data for the past year. That's overkill. I don't need that much data. So there's a sense of order of this forecasting is how long back do you look? Okay, so you have to look at some historical data. How far in the past do you look? That's in sense of order. So you want to forecast xt plus one. You're at xt. This is called the order. So let's say you go from xt minus p. This is called order p. So you look at past, you look at p time steps. You say I'm going to use all of these to forecast, right? To do a forecast for the next one. Okay, so the benefit is if the longer it is you look, you have more data. So in some sense, you should be able to do better for forecasting for the next one. But the more sort of higher order you look, you also have a lot of data that may not be relevant. It become a more difficult problem to forecast next one. You may have sort of irrelevant data that you don't need for forecasting. So there's a trade-off between that you want to capture enough history to be able to make a forecast versus not having too many orders making things complicated. Right? In the homework, you have an example is you cannot have the order being too large. You run out of data. You don't have that much data to look at. Okay, so it's a balancing act. It's asking to test out this kind of, what it should be. How many orders do you think? Okay, so for people doing a good project on this, let's say you're forecasting, household load, right? This is actually a question you have to think of. I have historical data. I want to know the load, let's say for the next hour. How far back should I look at? Do I want to give, last month of data? Do I want to just give the last day of data? Do I want to give the last 2 hours? Should I engineer a more advanced feature? Maybe I should look at past last week, but just at this particular hour. Maybe that's a feature I want to use. Right? These are the things that you can start trying. to see what happens in the project, right? Okay, so you have a goal, you have some data, you say, I want to forecast household power consumption for the next hour, then try, right? See what happens. I've used just last day's data. Is that good or is that bad? Again, if that's good, you're done. If that's bad, think of other things you can try. Think of other features you can engineer. Rarely that just throw every data into it and something intelligent will come out. That doesn't happen. Even if you're using sort of very advanced learning techniques, you cannot just say like just throw all the data into it and hope something good comes out. There needs to be some sort of menu engineering into this kind of either looking at the order or looking at some other features that you want in the forecasting algorithm. These are the things to try. Okay, good. Any other questions? Okay. Yeah, good. Yeah. It cannot be the same input, right? You have a deterministic model, right? So it's different to the same model. It's the same model, different data, right? Same model. You train a model, then you have a different data set to see how well your model performs on a different data set, right? So if you're doing linear regression, when you do training, you get the coefficient. Now the coefficient doesn't change. That's your model. Then when you do testing, you take another data set, that's your testing data set, and see how your model performs on the testing data set. Yeah, that's basically the idea. So it's the same training set just gives you the model. Then you use the testing data set to see how well your model performs in the testing data set. Right. So, mhm. Okay. Actually, then let me take a look. Yeah, let me take a look at it. Okay, let me take a look at that. Yeah, but the idea is the training should just determine the model, then testing tests how that performs. Other questions about this? Other questions? Okay, so the idea again for all this is to get a data set and just look at it, play around with it. Right? See what's in the data set, see whether again how a very basic algorithm performs for a data set, for the data set you have. Yeah. All right, okay, good. So let's continue with the lecture then, right? So if you look at forecasting, right? So here everything is real number, right? So classification, which we started last time, is a case where things are not real numbers, right? So you want the outcome at least is not a real number. You want the outcome to be a 0, 1 label. So again, you have some box, right? So you have some input X, you run it through your learned model, and you have output Y. But in this case, Y takes that of discrete points, right? So this is, uh, let's say this can only take value 0, 1, 2, 3. Okay, so Y is not a real number. Now your output is not asked to be a real number anymore. The output is asked to be along a discrete set. This is a very natural application, right? So it's a very natural application. In power system, that's most common is whether you have to determine sort of fault or no fault. Right? So 0, 1 is you declare whether there's a fault in your system or there's not a fault in your system. Yeah, right. So, and right now, the fault detection algorithm we have in our systems are quite simple, they're all hard-coded into the system. So they're false, they're sort of, they're not very smart in detecting faults. They're basically constructed to be very conservative. A lot of times when it's not a fault, they'll just say it's a fault. But this is used quite a bit in Power, this for classification. Yes, no question. And this comes up in a lot of other situations as well, right? So if you look at computer vision, it really got started by, can you recognize handwritten digits? So you handwritten digits from 0 to 9 can classify that, right? So this is really where a lot of this deep learning got started. As I give you, let's say, some image, can you tell me which number this person is trying to write down? Okay, again, the only thing that makes sense is this categorical output. Okay, this categorical output is not, you're not looking for a real number at the end of the day. Okay. So, but even though your output is a discrete set, what happens is normally all the operations you do are still continuous. So this only happens as the output. So normally the way these things look is you have X, this goes through something, some real number will come out of it, and then some other box will convert, let's say this to a discrete set. This will convert this to a category. Okay. So even though you need discrete numbers to come out of this, normally you only do this as a last step. It's not like you take you take X, and then you just start working with integers. Integers or category numbers are hard to work with. We only want to work with them as a last step. Okay, so everything else is just real numbers. This is all real numbers. You do adding, subtraction, multiplication, whatever here. Then at the end, you try to convert your real number to some category, to one of these categories. Okay. And normally what this takes is you can interpret this as a probability or proportional to a probability. And you look at which one of these is most likely given this probability that you have. Questions about this? So this is the broad idea, right? So even if you want discrete for outcomes, is you only get things to be discrete as the last time step. In the middle is all continuous. Right? Everything else is sort of continuous real number, operation based on real numbers. Right? Okay, so you look at most of the equation and the math will write down. You only get to, only as the last step you get to here. So again, you want to interpret things. This is interpreted as a probability or as a likelihood, or so you want to assign a real number to that. And the logistic function that we introduced last time is basically a function that assigns a probability. Right? So if you give a real number, the outcome is a probability associated with that real number. So logistic function is this kind of function, 1 plus e to the minus z. Okay. And this function takes value within 0 and 1. Right? So this is, if z is very large, this is very small. And then if z is very large, this is close to 1. If z is very small, this is very close to 0. Okay. Okay, so this is the function that takes value from 0 to 1. And the way you're going to use this function is basically the following. We are going to think of x as the input to this function. So the reason this is called logistic regression is the function ends up being used this way. You're going to think of this as your input, this as your weight that to be learned, right? You're trying to learn this weight, you're trying to find this weight. And then the outcome here, this is you want to interpret this as a probability of the outcome being 0 or 1. So basically you take some input, which is a real number, a vector of real numbers. You multiply by some weight, you learn this weight. Then you can plug into this function. this will come out to be either 0 or 1, right? So this gives you a probability of 0 or 1, right? How likely is it to be 0 or how likely is it to be 1? And then you use this probability to determine the outcome. Right? So this is the idea of using logistic functions. Right? So any question about this function? Any question about this function? Okay, so if this is your function, how do you actually output a discrete value? Let's say you got some weights. Let's say you determine this weight, so you determine W. Now I input X, right? As the output, I actually want 0 or 1. I don't want the probability of 0. So what do you do? Right. Right. So if you have a probability to actually get output, you basically just say, is this probably larger than 0.5 or smaller than 0.5, right? Is the probability of what larger than 0.5? So if the probability of the output, you think the output being 1 is larger than 0.5, we just say the output is 1. If the probability is less than 0.5, you say the output is 0. Okay, so you have a confidence. This basically gives you a confidence of which way it is. Then you just compare which is more likely and declare the alpha being the more likely one. Okay, so there's very easy to get a continuous number to a discrete number. What we do is just threshold. So there's nothing magical happening here. Just look at which one has the largest probability, declare that's the case. Declare that's the truth. Got it. Right, right. Right. So what if you have 10 classes? That's a good question. That's not very easy to do with a logistic function. It doesn't have 10 outputs. It's very easy to do with something like a neural network. Basically, you just have output that starts vector of 10, vector of size 10. Each coordinate being each component being the probability of the alpha being one of the categories. Read out the probability that's the largest. Let's just read that thing out. Okay. So the binary classifier, you can also do that. You can do a 0 more likely than 1 through 9. Right? You can do this sort of, iterative comparison. You can still do it. But that's why neural network is easier to work with. We'll look at neural networks later. But for now, think of this as binary. So we'll just declare. Okay. Okay. Sir? Yeah, so 0.5 makes sense, right? Otherwise, you're biasing your output for one or the other, right? So you don't want your decision root to bias output. You basically your training, your learning happens here. Then you want your decision root to be fair, right? That's 0.5. Okay. Right? So basically, if you change your decision root to be, let's say 0.4, you have different weights. The weights will try to be different. We'll try to bias this. Right? So you just have your decision root to be 0.5. Right? So here again, when we do this kind of learning, when we look at the performance, basically a lot of times we just look at did you get 0 or 1 correct. Often we don't associate the probability with it. Right? So when this kind of machine learning algorithm output a number, it normally does not give you a confidence around with it. If it gives you 1, it doesn't really tell you is it 0.0999, I convert to a 1, or there's just a probability being 0.51, I claim this as 1. Okay, so that we're not, normally is not outputted by the algorithm. Okay, so when you look at this kind of algorithm, most times you just look at, did you get the final answer correct? Not the actual probability being correct. Okay, so that's something to keep in mind when you look at this kind of algorithm. Okay. All right, good. Right, so when you have optimization problem, basically, we're going to think of the probability, right? So I think the probability, right? So the probability of output being 1, right? So we're going to think of binary data. So it's either 0 or 1. So let's say probability of being 1. This is given some x, 1 plus 1. So this is just what we have under the bottom, right? So you evaluate whatever this is, you declare this a probability. But this doesn't line up with the data, right? So the reason is this is not a trivial problem, or this regression is not a trivial problem, is we don't have probabilities in the data. What we have in the data are just hard labels 0 or 1, right? When the data we have doesn't have probabilities associated with it. So our data set, okay? So this is something to appreciate is when you're doing, let's say, something like linear regression, the data you have is just real numbers. So you can, take a difference, look at how far away you're from it. We're doing something like classification problem. Your data is just 0 or 1. It doesn't tell you what the probability is. Okay, so when you look at electric power grid, we'll tell you whether there is a fault or there is not a fault. The data doesn't come with how likely I think there is a fault. Now, that's not what data is. When you look at image recognition, it shows a picture. It is a picture of a cat or a dog. It's just two labels. The human is not going to label you with 95% probability, I think this is cat. But all your labels are just 0 or 1, okay? Not probabilities. But here, the output of your algorithm is a probability. So there's a mismatch of where your algorithm is outputting versus your data. Okay? So there's a mismatch there, right? So is that clear? Is that clear where the mismatch is? Okay, so you would like the probability given to you. That's not given to you in any data set. Okay, so somehow you have to think about how do you measure how good this is. Okay, because you don't have access to probability, right? That's not what the data is. Okay, so you have to think about, how we need to come up with a loss function. Okay, so the loss function people come up with is sort of very intuitive, right? So you have, let's say, you have true data, right? You have data, a pair x, y. This is a label. This is either 0 or 1. Okay, so what do you want to do, right? So you want to say is, if the label is 1, what do you want? You want py of x to be large, right? You want the probability to be large. You want the probability, if the actual label is 1, you want to be very confident that this is a 1. On the other hand, if the label is 0, you hope you want sort of p of y of x to be small. Right? You want this thing to be close to 0. Okay. So if the label is 1, you want to maximize what this number is. Use the label 0, you want to minimize what this number is. That's how you measure how good your label is, right? So if the label is 1, it's not sufficient for this probability just to be a little bit more than 0.5. You want this to be as close to 1 as possible. If the label is 0, you want this probability to be as close to 0 as possible. Okay, so you give this kind of weighting. So we want to maximize py of x if y is 1, all right? If your label is 1. And you want to max 1 minus p of y of x if y equal to 0. Okay? All right, so again, if your label is 1, you want this to be large. If your label is 0, you want 1 minus this number to be large. Okay. So is this clear? Is this a goal clear? Right. This is your goal. Okay. So now we'll do a trick. We'll do a mathematical trick. It turns out P, this probability, is not the best object to work with. Okay, so we'll work with another object. And an object we'll work with is we'll work with minus log p of y given x. So this is the object we'll work with. There is sort of mathematical reasons why this is a nicer looking thing. But suffice to say as log is a monotone function, right? So log is a monotone function. Log of x is large if x is large. Log of x is small if x is small. Okay. So I'm just replacing this value with, through a monotone function. So this just be mathematically, this is just a better function to work with. We'll see why. But now we're doing now is instead of working with this number directly, we work with log of this number. The reason doesn't change. The reasoning doesn't change. We're just going to log this. The reason we're going to log this is we'll relate this to entropy later. Okay, so that's just, we'll just start working with this log number. And this happens a lot. Very often in this kind of problems, instead of working with the object itself, you want to work with the log of the object. This is very often the thing you would do. So you log it. And so taking log, so basically if p of y of x is large, minus log p y given x is small. Right? So if 1 minus p y given x is large, minus log p. Okay, is small. Right? So basically what we want to do is want to minimize minus log of something. We just want to minimize minus log of this thing. So our goal is to want to minimize the following. When the labels are 1, we want this number to be small. Okay, right? So when you're summing over all the data where your label is 1. In this case, you want the p of y of x to be large. So you want the log to be large, and you want the minus log to be small. Okay, so you're going to minimize over this objective if the labels are 1. Right, so this is just a mathematical trick. Right, so this is just a mathematical trick we'll do. But again, turns out this is just a better form of the optimization problem. Okay. Does this make sense? Does this make sense? Right. So maybe not why you're doing this, but at least the minimization problem should make sense. Okay. So similarly, when you look at y equals 0, then what you want to do is you want to minimize log of 1 minus p of y given x. So this is the other part, right? So if your label is 0, you want this to be small. So you want 1 minus this to be large. You want log of the thing to be large. So you want minus log to be small. So you're minimizing this whole objective, basically. Okay? So you want to find the weight, W, that minimizes this thing. This is your goal. You want to try to minimize. Okay, so that's our goal. So our objective is now this sort of weird looking log thing. Right? So let's not worry about whether we can optimize this or not, but this is our goal. This is what we want to do. Okay? So this is very different in some sense in linear regression, where you're just summing up the error, right? You want to minimize the error. Here, you're actually breaking apart into 2 different categories, 1 or 0, and each of them gets a different looking loss function. Yeah. Questions? Any question about this? Okay, so you do this. Right, so the trick is now is to look at this two and say, okay, I have two summations, and they're summing over this kind of indices, right? This is y equals to 1, this is y equals to 0. This is not that easy to work with because this requires you look at through the data and break it into sort of two distinct piles. Okay? So can anyone think of a way to write this two summation into one summation? There's actually a trick to do this. Is there a way to combine these two? Instead of summing over distinct classes, I sum over one summation. Right? So this is a trick that people do. The trick is the following. As we're going to use the indicator trick. This is an extremely fancy name for the following fact. As you look at, right, so this is the fancy name is because now what you can do is you can sum over all points now. You can sum over everything. So what do you do when you sum over everything? Well, this is okay. So this is the indicator trick. Basically, you added this y multiply into the front. So if y is 1, you pick up this term goes away. Right? So y is 1, this term gets completely killed. You're just minimizing over the first term. If y is 0, this term gets killed. You're just minimizing over this term. Okay? Just minimize this term. So this gives you a way you can write it into so this way you can write it into a single summation. Basically, this is called the cross entropy loss. So there's a name for this. This is called cross entropy loss. And what this loss does is this is a lot of theory behind this one. There's a lot of theory behind this. Okay. The reason you want to get into this cross entropy loss is if you go back to the function that we picked, right? We picked the logistic function. And the justification I give is, well, if you look at this function, it takes a real number and mass it between 0 and 1. Right? This is sort of the reason I give, because I want to interpret this as probability. That turns out as not a great justification. There's many functions you can take. You can throw in a real number and get it between 0 and 1. There's an extremely large class of functions you can do this. Can you guys think of a function that takes a real number getting to 0 and 1? That's not this one. Right? So for example, you can take sine of something and add 1 to it. Add 1 divided by 2. Nothing will be between 0 and 1, right? So that's a good, right? So the reason you need cross entropy is, right? So instead of, I can take sigma z to be this function, 1/2 1 plus, yeah. This function, you put out anything in, right? So this is between minus and 1, 1. You add 1 to it, it's between 0 and 2. You divide by 2, this is between 0 and 1. There's another function that take a value, spit out 0, 1 to it. This, for example, is not a very good function. This is not a great function to use. It's not a very good function. There are other functions you can use, right? So this is actually not a terrible function. Okay, there's a worse function you can use. The worst function is the following, is you can take, okay, so if z is between this, 1 if z is greater than 1, 0 if z is less than 0. That's another function you can take. You basically take a number threshold. Okay, anything larger than 1, you just say it's 1. Anything smaller than 0, you say it's 0. There's a good and perfect, from the reason I give, those two works equally as well as a logistic function, right? It takes a number, it spits out 0 and 1. Again, this is a terrible function to use. So to know this, you actually need to go through this cross entropy loss. Okay, why this is the right function to optimize. There's a reason behind why the logistic regression is the sort of the right regression you want to look at. Okay, why that function sort of we picked, seemingly just randomly is actually the right thing. That requires getting to this loss. Most of the packages you use, for example, in Python, minimizes this thing. Okay, there are again reasons behind it why this is going to work. So again, any of the books you read and in the paper you read will say, we minimize cross entropy loss. If you go read any sort of the machine learning package, you'll say we minimize cross entropy loss. It's just this thing, okay, just minimizing this. All of this is saying that is basically you want to say yi is 1 makes the probability large, yi is 0 makes the probability small. That's all I'm trying to do. But there's sort of a lot of reason why. Why the logistic regression is a good idea. That's a good regression. Okay. And you look at things like for vector machines, neural networks, and all that sort of has its roots in this kind of idea, minimizing this kind of loss. Okay, so for any of you more interested, just Google cross entropy loss. There's a lot of things you can read on there. But what happens is we want to rule out these things. These are the things we want to rule out. Okay? We don't want to use those functions. All right, any questions about this loss? Yeah. It's still for binary, right? This very much uses y has to be 0 or 1. It very much uses that idea, y is 0 or 1. Okay. Right, so implementation will not optimize this, right? So anything will solve the optimization lots of ways. Okay, there's lots of ways to solve the optimization problem. Any of the package we've been using in the homeworks will solve this. You basically change the command from linear regression to logistic regression. Will just minimize the cross entropy for you. So we are not again going to worry too much about how this is solved. Suffice to say, this is not a very hard optimization problem. Lots of algorithms can solve it extremely fast. So what we care about is when W is found, the decision rule is okay, so that's our decision rule. So we're not going to, once we found W, then basically you can compute this number, compare to 0.5, output this, okay. And you can put this equal sign, right? So this is greater or equal to 0.5. Yeah, got it. Yeah, logistic function is a sigmoid. This is sigmoid, yeah, sigmoid, yeah. Sigmoid is another name for this. Okay. Okay, any other? Good, right? So you can put this equal sign anywhere you want, okay? So it can be put into this one. You can have this less than equal to 0.5. Doesn't really matter, it's convention. You can say if this is equal, flip a coin. You can also do it that way. But so the equal sign goes wherever you want it to go. Okay. Although to note, this thing being exactly 0.5 happens more often than you think. Right? So this is not always a sort of accident, right? Very unlikely accident. You get to 0.5. You get to sort of something that's 0.5. This can happen quite often. So how does 0.5 happen in this case? Like how will you get 0.5 out of this function? Right? So to get 0.5, you have to be 1 over 2. So this is 1 plus, you have to get 1 plus 1. So you have to get e to the 0. So what happens is this inner product has to be 0. If you have vectors, right? So you have two real numbers multiplying each other. It's hard to get 0. One of them has to be 0. If you have two vectors looking at the inner product, it's not very difficult for this to be 0. They just to be orthogonal to each other. They just have to be orthogonal, right? So you have high dimensional vector. You multiply by another vector. With high likelihood, they're actually fairly orthogonal to each other. So it's often that this thing is actually closer to 0.5. Depends on how high the dimension this is. Okay, so this basically give you the sort of geometric interpretation. As you have W, you're basically looking at as X making a right angle, is making a acute angle, right? What is the angle of X making with this W? Depending on this angle, you're trying to classify this. And as possible, you just make a right angle to this. Okay, in high dimensional space, it's very easy to make a right angle. It's very easy to make a right angle. Right? So this could happen. Like it's given data, it's not hard to engineer. This can happen. Okay, right? And you see all of this sort of examples thing. I don't know if you guys seen this kind of machine learning examples. Is let's say you have some picture of a dog, and you change a few pixels. Now suddenly the classifier thinks it's a cat, I think it's a person, or think it's something else, right? Or you have a stop sign, and you change a few pixels. The human still sees this as a very clear stop sign. Then they say stop driving car, we'll see this as go, or speed sign or something. The reason is, in all these cases, X is very high dimensional. Right? Very high dimensional. You're multiplying two vectors. This sort is not that far away from orthogonal. You change a few numbers in X, you can make those two vectors essentially orthogonal to each other. And then your classifier just guessing random things at that point. Yeah, you basically have a random classifier. Okay? So I should pay it. Again, when you look at these two numbers, think of X as hundreds of dimensions. W is hundreds of dimensions. Okay? So you multiply this kind of numbers. And really the geometry is most high dimensional vectors are orthogonal to each other. Yeah, that's sort of how geometry works out. Okay, so that's something to keep in mind. Okay? So again, it's not, don't expect this thing comes out to be always close to 1 or close to 0. In practical application, a lot of times it's just like very close to 0.5. Okay? It just happens for this kind of data. And that's where sort of a lot of challenge in the learning algorithm is, because the dimension of these things are so high. You're looking at very high dimensional things that's essentially close to being orthogonal to each other. Okay? All right, so if you look at this rule, right? So if you look at this rule, it's actually an easier way to evaluate this, right? You don't need to evaluate 1 over 1 plus e to this thing, right? What you can do is you can just directly evaluate this inner product, right? I don't need to, this is a monotone function, so, right? So know that 1 plus e to the minus this thing is greater or equal to 0.5 if and only if this is larger than 0. Right? This is the only way. Or this is larger than equal to 0. Okay, so this is the, right? So if this happens, that happens. So 1 over x is less than 0.5 only if x is less than 0. Right? So this is the, right? So when you write the code, you can evaluate this thing, or you can just take the inner product. These two are exactly equivalent. But here now you have a very clear geometry to this. Basically, this gives you a very clear, yeah, actually input actually. Yeah. Oh yes, yeah, X can be a matrix. Yeah. Yeah, so X can be a matrix, a vector, a number. So a matrix is nothing but a very long vector in some sense, right? So as long as I can take an inner product, then it's okay. Yeah. So for example, right? For example, a matrix, right? So let's say let's say X as an image as a uh, a picture, let's say. Okay, so what is a picture, right? So that picture, let's say, basically you have a very small picture. So this is 16 by 60. Let's say your x is 16 by 60. Okay, so what a picture is basically this is a matrix. You have pixels in the picture, right? So let's say you have a picture. Normally you can have so 16 by 16. Okay, right? So you have 16 by 16 picture. Then each pixel you assign a value, right? So it depends what kind of picture you have. Let's say now you have a grayscale picture. So in grayscale, it's black and white, right? So it's sort of just black and white picture. Grayscale, there's a value ranging from 0 to 8, or 0 to 7, denoting sort of how white or how black the thing is. Okay, right? So let's say you have a grayscale. So each pixel is 0 to 7. Okay, each pixel takes a value. Right? So it ranges from 0 to 7, depending on sort of how exactly grayscale you want to be. And this is you can very easily turn this into a vector. This is just a 256 long vector. You can turn this into a vector. This is each element taking value from 0 to 7. So you can just do a linear product, right? Yeah, you can flatten, right? So you can flatten. You can, sure, yeah, sure. You can flatten this in a column row vector, right? So this is how your computer will do it, basically, right? Well, no. So to your computer, the matrix array is not fundamentally different. There's a bunch of numbers you need to multiply together. So at the back end, it will multiply however it wants to multiply. Right? It's multiplying to a bunch of numbers together and adding it up. Right? So you can, in your mind, right? So you can either directly interpret this as a matrix, multiplied by a matrix, adding it all up, or think I'm converting this to a vector, doing the standard dot product. Okay. Right. Right. So when you write code, you don't have to do that. The package at the backend will do it for you. But in your mind, it's easier to think of this dot products vectors between vectors. Then think of this image as flattening into a vector. Yes. Okay. Any other questions about this? Okay, so this is a grayscale. What happens if you have a color picture? How will you do this? Let's say you have an RGB picture. What happens here? How you think about this picture now? So here, a grayscale picture is just a matrix with values. So you can flatten into a vector. What about now you have color? Let's say RGB, in the picture. Right, so still it's the same thing, except you multiply the size of matrix by 3. Right? Instead of assigning one value per entry, you assign 3 values per entry. One of them is R, one of them is G, one of them is B. You can still take this, flatten the whole thing. This will just be 256 times 3, a longer vector you have to work with. Guessing all those things, so you can think of everything as vectors that eventually gets worked with. Yeah, yeah. Right. Oh, cross entropy? Okay, yeah. So cross entropy is specifically this function. It's called cross entropy. This is the one we optimize. Now your question, right? So we optimize this thing. This is where your computer is doing with optimizing over W. You're trying to minimize this function. There's reasons for optimization reasons why that's much easier than directly working with this numbers. Right? So technically you can just directly work with this. Yeah. Yeah, when you use cross entropy, optimize is much better. The W you find is much easier to find optimal W. Much easier to find optimal W. Yeah. There's a reason. Yeah. Go ahead. Yeah, oh, yeah, that's a scalar, right? It's a inner product between two vectors. Yes, yes, yes. So the vector is the same length. Yeah, vector same length. Yeah, vector. Okay, good. Right. So yeah, so you don't directly optimize over this, right? But once you find this W, you can just directly work with this. Okay, you don't have to care about how you got this W. This is gotten by optimizing cross entropy. Once you find it, you can directly look at this product. And for most info you have, is basically you can convert into a vector. It's a very long vector. Think about now people are doing this using movies and stuff. You classify movies using AI. It's just an extremely long vector, but still it's a some vector that you can do in a product. Yeah. Right. You don't have to do it. Your computer will do it for you. But yeah, but you can think of this one. Yes. Yeah, you can think of it. Yeah. Yeah. Right. So you really want to get really mathematical about this. As these two are some object in the inner product space. If that sentence makes no sense to you, think of this as vectors. Just some vectors that you have. Okay, so there's some vectors. You can now, the good thing about these vectors is they actually give you a very nice geometric picture. So let's think of now, let's take an example. Say, say you optimize, right? Let's say you optimize in a two-dimensional space, your W becomes 1, 1. Okay, so and X is in R2. Okay, so you're some two-dimensional space, you have two inputs, and the ways you got is 1, 1. It's just this 1, 1 way to go. Okay, so how does your classifier work? Right, so how does the classifier work? So let's say this is X1, X2. We're interested in this W transpose X. Okay, we're interested in this vector. All right, so now so what does this mean geometrically? Well, so let's look at when this is 0. So what are the x's that makes this thing 0? Right, let's say look at the boundary case, right? So boundary case is when this inner product comes out to be 0. What does that look like? What is x1 plus x2 equal to 0? Right, so let's say this case, this is x1 plus x2 equal to 0, right? So that's your inner product in 0. What is this? Geometrically, what is this? What is this? It's a line. What does this line look like? Right, so line goes through the origin, looks like this. This is basically your line. So this is your 0 line. Now, which side of line is W transpose X larger than 0? So is this side of the line the unit product larger than 0, or is this side of the line the unit product is larger than 0? This side. This side is what happens. This is where, so that side of the line, you have something greater than 0. The other side of the line, you have less than 0. Okay. So basically, what this classifies thing is, If you look at the point in R2, if it's on this side of the line, we're going to classify this as a 1. If on this side of the line, we're going to classify this as a 0. Okay, so this is basically geometrically what this comes out to be. You always have a line because this is a linear, something multiplied by x equal to 0. So you always have a line. And then basically now you're looking at is which side does this point fall into compared to this line. Okay, that's all your classifier is doing, right? So any question with this picture? This geometric picture we have? So this is the essence of classification, basically. You take some input. You want to convert this input now to a scalar number. The easiest way to do it is just multiply it by a vector. Right? So I have a vector as an input. And I need to get this thing to a number. How do I do this? I multiply by another vector. I look at, is it larger than 0 or is it smaller than 0? Different W's define different lines. Right? So if I change the coefficient here, I define different lines through the origin. I define different classifiers. But all this classifier is, this is a linear classifier, and you're looking at which side does the point lie on. Okay? That's sort of all there is to it. The whole goal is to find this line that separates the point the best. Okay? So if you look at an example here, right? So let's say here you have some blue points, some red points. So you can think of blue, let's say labeled 1, red labeled 0, if you want. Now you're asking, okay, I want a good classifier based on these are the points and labels I got. I got these. So where does the line have to be? So if you actually solve the optimization problem, we'll tell you this is a line. So anything above this line, you classify as blue. Anything below this line, you classify as red. Okay, so there is all there is to this line, okay, to this process. They're trying to find where this line is. So this two-dimensional case, this is a line. This is a line. Right, so the line separates the space into two planes, if you want to think of it this way. But your classifier is this line, right? You want to know where the boundary is. So in higher dimensional space, it's a hyperplane. Right? So in the R2, it's just a line. Questions about this? Okay, so your next homework is basically something like this. You'll be given a bunch of dots, ask you to look at minimize cross entropy, which is your computer will do it for you. And then the day you get a W, right? And the homework asks you to do is draw the line. What draw the line means is, draw a picture like this. Okay, draw that picture. The question is, draw the result graphically. This, right? So draw something. Depending on the question, either like this or like this. Right? This is what draw the result means. Okay. So for those kind of classifiers, that's in R2, what typically happens is you draw the classifier. Okay. There's a clear geometry within the classifier. Okay, right. So this is the basic idea. Okay? This is just the classification. So as before, you can do regularization. Right? So it's very similar to before. We can do regularization. Right? So we can have mean. Right? So this happens. This form is used very often. Is again trying to make this coefficient reasonable. So you don't want your coefficient to be very large. And you don't want this to be super large. So you normalize it. So this regularizes a sort of size of the coefficient. very similar to before. We can also so we can look at so you don't have to always look at just X. You can pass this through some nonlinear features and look at nonlinear features. So this is again the optimization problem becomes sort of harder to solve. But for us, we don't really care about how the optimization problem is solved. The geometric picture is very much the same as before. Okay, good. All right, so this is your cross entropy training. Okay, so the good thing about this cross entropy loss function is that mathematically it makes a lot of sense. You want to train with this one. You want to use this in your optimization problem. The bad thing about cross entropy is with very high probability, the people who's paying you may have no idea what this is. Okay, so that's a question in this class is why are we trading with this weird looking object, right? So we're not even gonna go into the math behind this. So if you go and tell, right, so this is mathematically good, intuitively very strange looking thing. What is the thing that we're looking at? So let's take a 5-minute break and we'll look at some more intuitive metrics we can report, right? Not just a cross entropy we can have. Okay, so I'll take a 5-minute break. We'll come back at 7:20. Okay, all right. So let's keep going, right? So, all right. So again, to make sure is we always train with this, right? With cross entropy loss. So whenever we say we do training, we are optimizing W with a cross entropy loss. Okay? The problem is that when you want to communicate the performance to other people, directly giving the cross entropy loss is not very useful, right? Because the reason is this will end up to be some number, okay? So let's say you work with this end up being a number of -5. What does it mean, right? Like what is the performance of -5, right? So unlike linear regression, you have a very clear interpretation of your loss. This is the distance between the actual data, actual label you have, and your prediction. Here, if you come across entropy, you say this is -2. What does this mean? What is -2? It's sort of hidden in the structure. So when you communicate to people, when we report the performance, we need other metrics. Okay, so we train, so we find the best W with cross entropy. We don't normally report this. Okay, so we don't normally report the value of the loss. It doesn't, it's sort of very hard to interpret. So we want some more easier to interpret metrics, right? So you're communicating, so a very actually realistic example here is a couple of years ago, we worked with Status City Light, where the idea is to predict that when you have a power outage, for example, how likely is that your power will be restored in an hour? Okay, so that's something people care about. They want to say, I have an outage, based on the information you know about this customer. They want the city to tell them, is it likely my power will come back in an hour? Okay, so what we did there is, we didn't use logistic regression. We used a more complicated algorithm, but still, you end up, training cross entropy loss. But you can't tell that to the customer in the city, right? That's not, you can't tell them that performance. You have to give some people, some idea where other people understand what your performance is. You know, some GTV, more intuitive ideas for performance. So that's why you have a lot of different metrics you report to people, right? Although you never train with this metrics. Okay, so metrics, the most common one. This is just accuracy. This is defined exactly how you would think it's defined. This is 1 minus number of mislabeled points. Right, so 1 minus the number of points you go wrong. Mislabeled samples. Okay, so this is just accuracy, right? Just how many you got wrong, divide how many you have. 1 minus this gives you accuracy. Let's say your accuracy of 0.9 means you got 10% of the label wrong. Okay, so this is, you almost always report this value to people, right? So I'm classifying whether I can restore your power within an hour. Let's say I have a classification accuracy of 90%. That means for 90% customers, I can, you know, if I tell them it's either within an hour or longer than an hour, I got it correct. Okay, so this is easy sort of metric people like to see. Okay. Does this one make sense? Okay. This is accuracy. Over total number of labels, yeah. Okay. Why is this thing insufficient? So this is the one that we always report, but this is not the one we only report. Right? We report a bunch of other things on top of accuracy. So this is normally not sufficient just to give this number. So why is this insufficient? Right. So the drawback of this is doesn't differentiate between which way your error is. Okay, this way, because the way this is counted is if it's zero, you label as a one, it's error. If it's a one, you label as a zero, it's the same error. Right? It does not differentiate which way the error goes. Right? So this doesn't, just doesn't differentiate the errors. So you don't, right? So basically this is 0 to 1 or 1 to 0. This counted the same. It doesn't matter which way you mislabel. Can you think of a situation where you do want to distinguish there? Like where you want to say that, you know, which way you make a mistake is important. It's actually not often where these errors are treated equally. In most applications, you actually want to sort of bias towards one way the error or the other. You really want to know which way the error goes. Can you think of some situations like that? Okay, so for example, in the grid, okay, so grid stability is often where now data science is used to detect whether grid is stable or not. So for this problem, the which way the error goes matters, right? So if the grid is not stable, you declare the grid is not stable. What happens is the operator will spend some effort on making the grid more stable. So you lose money, but it's okay. As a customer, you wouldn't even notice it, right? It's just, you know, you waste a little bit of money. Now, if the grid is not stable, and you actually declare the grid being stable, what happens is you have a blackout. Okay, so that's a much worse outcome than the other mistake, right? So there's one mistake that's much worse than the others. Okay? Another setting, this is sort of healthcare. For example, when you do something like a cancer screening, right? Or actually, closer to us is a COVID test. If you do antigen COVID test, the error is biased towards one direction. If you're positive, it will say you're positive. If you're negative, we'll also more likely say you're positive because it thinks the errors are weighted differently. Okay, so healthcare, you do a cancer screening, right? If you don't have cancer, saying you have cancer is inconvenient, but maybe not life-threatening. You do a follow-up test, you can figure that out. If you have cancer and screening says you don't have it, then it's a much worse outcome, right? You may misdiagnose somebody. Okay, so those kind of situations you don't catch by just looking at accuracy. Accuracy treats two of these exactly the same. Often in many situations, accuracy is by itself not good enough, right? So you always give this number, right? So whenever you do this, you always report this number. When you report something on top of it, you report sort of type 1, type 2 error. You report false positive, false negative error in addition to this. Okay. And yeah, so which way it matters? This is sort of, so you can, in addition to this one, you can define a lot of other metrics, right? So you can have sort of true positive, right? So you can have, different, which way you're missing, right? So false positive is a negative sample classified positive, false negative, the positive sample classified as negative. Right? So which way you're looking at this. And you can summarize this. You can look at things like precision. I don't know how they came up with these names, but this is a true positive over the true positive plus a false net positive. Okay, so this is your precision. This is basically saying among all the positive things, what fraction did you get correctly? Okay, so this is all the positive things you have. How many of them, what fraction of them did you get correctly? This is, you can have recall, which is the other way. This is a true positive over the true positive plus the false negative. Okay, so recall is basically the things that's actually positive, how much did you get correct? This for the other things you classify as positive, which fraction of it is correct? Okay, so normally you can report these two numbers. There's just a measure of different metrics of which way the error you make. Okay. They don't always make sense, right? They don't always make sense. But this is just, so you could define both of this with negatives, true and false negatives, but they're equivalent. So you can swap positive negative here. Right, so the thing to note is you don't want both of them to be small, right? You can make one large but another one small. So then you define something called F-score. This is called, so F-score, this is just F, precision, times recall, yeah, precision, plus recall. Okay, so this, you can report F-score. So if F is large, both of these are large. Right? So both are close to 1. Right? So this is good. So if one of them is very small, F will be small. So often when you report, you just report F-score. And these are all the things you report, right? So to us, it's not, we won't overly interpret these. This is just an example showing us sort of different other things you can report in addition to the accuracy. Okay, so normally you don't just report the accuracy, you report some combination of these things, depending on which one you care about. Okay. So whenever you look at the performance, again, you always optimize the cross entropy loss function. You report these numbers. So it's a little bit weird in this case. Yeah, go ahead. F is just that function. It is defined that way. Yeah. I don't know what it stands for. Like, I don't even know why this is called recall. It's just some name they gave it to it. And I think about this time, you really run out of names. I don't know what, so this may be related to the F statistics in the statistical test. I'm not 100% sure, but it's just called F score. It's just the name. We run out of names. Yeah. Good. Right. So that's a good question, right? So the question is, if I report these things and not the cross entropy, why don't I just optimize these, right? Why don't I just optimize recall? Or why don't I just optimize the F score? Why bother optimizing cross entropy? Why not directly just maximize this thing? Any something of a reason? If when you report to people, when you communicate to people, let's say you give them this F score, you give them the accuracy, why not directly optimize the thing you're telling people about? Right? So in linear regression, we want to minimize the error, and we tell people the error. This is what we minimize. In here, why are we minimizing one thing and reporting something else? So nobody actually maximizes F score. Nobody actually directly tries to maximize accuracy. But why? There's two reasons. There's two reasons. One reason is just from optimization point of view. This thing is hard to optimize. Okay, remember when you say optimize, I have to find a W, right? That the makes the functional value. If I'm doing F score, I have to find a W that makes F score. That is a non-trivial optimization problem. It's not that easy to find a W. So that's one reason mathematically this is hard to work with, hard for a computer to optimize. The second reason is that when you report all these things, these are all competing objectives. Accuracy, which you care about, and F score are two different objectives. So it's hard to say which one you optimize, right? If you optimize accuracy, your F score may be very bad. If you optimize F score, your accuracy may not be so good. So in some sense, cross entropy is the right trade-off for all of these things together. So when you optimize cross entropy, you sort of make all of these fairly good. You can formalize what that means. So if you look at that. But turns out is because you want to report so many things, turns out we should optimize this for cross entropy for a mixture of these things. That makes everything look good, basically. That's what cross entropy does. Normally you cannot take off one of them just to optimize this. That you cannot do. Yeah, yeah. So in cross entropy, what you do is the functional form doesn't change, right? There's nothing you can do about the functional form. So in most cases in practice come down to is you either tune this lambda, how you regularize the system, this has a big impact, or you find the right nonlinear features. This has a big impact on cross entropy. The functional form of the thing you're minimizing doesn't change, except you add a regularizer. So most times in practice, what you do is you either expand the features you have. Okay, you can expand how many features you have, throw in more features, and see if that does better. You can find different functions operating on this feature to make it better. So for people who heard of things like convolutional neural network, that's basically all it's doing. They're taking an image, saying let's not just directly look at this as a big vector. Let's do some operations on this image first, and then look at this thing of this sort of result of that operation. That's basically applying this function first. Okay, so most in practice is find a nonlinear feature, find some better function. Okay, so convolutional neural network does this. This transformer, the hottest thing right now does this. Because all of them is can I do this better? You're not touching the cross entropy metric. That normally you don't touch. You basically come to here and see what are the different features I can find. Okay. So A good example is, for example, nowadays, if you look at a lot of electric vehicles, the problem with electric vehicles is uh, batteries may catch on fire, or batteries may die when you drive electric vehicle. That's actually not uncommon for it to happen, especially in sort of more commercial vehicles. So a very big hot topic in EVs is, can I predict what will happen to my battery? Can I predict a battery failure? Can I predict a battery that's dying on me? There, the name of the game is, can you engineer and measure different features? So everybody has temperature, voltage, current. Everybody can measure that. Questions, can you measure other things? Can you measure other chemistry? Can you sense a faster time scale? Can you do sort of processing when you actually take those measurements? All of this basically comes to engineering this. That's in practice what you do. Where a lot of gains come from is engineering these features. And this is again problem dependent. There's not always a sort of the best features to use, but problem dependent, you engineer this feature. Right? So when you report to people, you still report these. You still report these. It's just that when you still report these, but you're not directly optimizing. Okay. If you work in data science for any of these projects, with a good high probability, your boss will tell you, hey, why don't you just directly optimize F-score? With very high probability, you get this question. Why don't you just directly, our customer really cares about accuracy. Why don't you just optimize accuracy? Why are you doing this for random thing and optimizing some other function? Okay, so that's the conversation. You work in that environment, you have to think about how you will have that conversation. Never directly optimize these things. It doesn't work. Okay, if it doesn't work on the test samples, it's horrible for some, right? So if you optimize this thing will be horrible. You optimize this thing, the accuracy may be bad. You optimize something, we'll do something like ROC curve, this may be bad, right? So you cannot directly optimize on these things. So you don't directly optimize a recall. So your boss comes and says, I really only care about recall. Can you please optimize recall for me directly? That's not something you can do. Okay? Or it's very dangerous to directly optimize this kind of metrics. Okay. Right. Good. Other questions? Okay, so the next homework in some sense will help you explore this. This is a data set, you optimize, compute all these metrics and see what happens in all these metrics. Okay. Again, yeah, so the thing, at least for engineering applications, is can you engineer better features? Are there good features you can engineer? Right? Are there good features you can engineer? Are there good features you can measure? That can help your prediction algorithm to be better. Really not much can be gained by, say, optimizing a different function. That normally doesn't gain you all that much. That's where the feature engineering is still more important for us. Okay, so the last thing here we'll look at is the ROC curve. The ROC curve says the following. The ROC curve says it's trying to measure how well you can do compared to a random guess. Okay, so ROC is, so when you have classification, what you can do is you can always randomly guess whether it's a 0 or 1. You can just do a random guess. So if your data set is balanced, then the random guess is actually not so bad. Okay, so let's say that, so suppose the data has same number of 0 and 1 labels. Okay, suppose I give you a data set. You didn't even look at the input at all. You basically counted the number of, look at all the y's. You figure out, hey, there's the same number of zeros and one. Okay, in this classification problem. Okay, and then we can plot this. So this is false positive. This is false negative. Right, so this is, oh, sorry. Let me plot this as a true positive. So this is, right, so this axis is And then how often you're wrong in the positive case, this is how often you're right. Okay. Unless I give you a data set that's sort of equally same number there and ones. Okay. What is the simplest algorithm you can do? And what is the performance of that algorithm? Like, okay, so let's say the data has equal number there and ones. Is there an algorithm that has no false positive? Can you give me an algorithm that says never has false positive? There's extremely trivial algorithm there. What is a trivial algorithm that never has a false positive? Okay. So how do you never have a false positive in your prediction? It's not a trick question. What is a trivial algorithm that never has false positives? You declare everything is negative, right? So I want no false positive. One way to have no false positive is to never have any positive, right? So it never output positive at all. Okay, so I give you a classifier. Whatever comes in, I output zero. Okay, I don't care what your input is. I'm going to output zero, whatever your input is. That classifier, by definition, never has a false positive. I cannot be wrong in the false positive setting, right? Because I will never classify a negative into a positive. Right? I just never output zero. Right? I never output one. Okay, so I always put output zero. The false positive rate is zero. I don't have a false positive. Right? Is that clear? How that works? Okay, so I'll explain one more time. Okay, so right, so false positive rate. This is a number of right. So this is sort of yeah. So let's just look at false positive. Okay, so this is a true y is zero. It's classified into one. Right. So the true y is zero. I classify into a one. Okay. I want a classifier where this never happens. I want a classifier this never happens. So I give you the following classifier. X into some box. This box, what happens is outputs zero. Okay? This is my box. There's a trivial box that whatever you put it in, output zero. I don't care what you put it into. This is a classifier. It takes the input, gives you one of the values in your binary classification, right? This is a dumb classifier, but it is classifier. Right? We all agree with this. Extremely dumb classifier, right? But what is the benefit of this classifier is there is never two false positives. I cannot have a false positive. There's just nothing positive ever comes out of this. Okay. All right, is that clear? Okay, so that's a false negative. No, that's all right. It's supposed to be a positive. I declare to be a negative, right? So I want to avoid this case. 2y is zero. I declare as a one. This is the only case I care about. Okay? I say this is the only thing I care about. I want to avoid this from ever happening. I claim this classifier, well, this never happens. Okay? Okay? So I want to avoid this from happening. Do we agree this classifier, for this classifier, this never happens? Yes, right? So I can never classify a zero into a one, simply because I never output a one. Okay, right? And are we clear about this? Yes. Okay, so again, it's a dumb classifier, but this is just a classifier. I'm just claiming for this dumb classifier, there's no false positive. Okay? There's no false positive. Okay? All right. So here, the false positive rate is zero for this thing. right? Because this event never happens, right? So this is this clear. This is again a dumb classifier, but at least it's good for this metric. Okay. All right, so this clear. It avoids all this event from happening. So let's be clear with this because it's very important how we draw that curve out there. So let's be careful. For this classifier, I can avoid a false positive. Okay. And this is also the reason why you never optimize just one of those metrics like recall precision and that sort. You tend to run into this kind of dumb classifier. Okay, sorry. You want to avoid something? I'll just avoid it. Okay. Let's just have a dumb classifier avoiding. Okay. So this has a false positive rate of 0. Right? I don't declare. I can never be wrong in this direction, simply because I never declare anything as a 1. But this also have a true positive rate of 0. Because if the y should actually be 1, well, you never actually declare a 1. Right? So this just outputs 0 all the time. Okay? It has a true positive rate of 0 as a false positive rate of 0. Okay, right? So what that gives you is gives you 1 point on this curve. Basically this point. Right? So in some sense, the smaller in this axis, the better, right? Because false positive rate is smaller. The higher on this axis, the better. The true positive rate should be high. Okay, so this point optimizes one direction, does horribly in the other direction. Okay, right? Does horribly in the other direction. Right. So now you can consider the other classifier. Outcome is 1. Right? In this case, as I don't care what you give me, I'm going to declare 1. I don't know. Okay, so what is the benefit of this classifier? This says that now the true positive rate is 1. Right? So I can never be, if the actual data should be 1, I will always be right. Because I'm just always declaring 1. Okay, so and the false positive rate is also 1. Because I'm just declaring 1. So whether it should be true or false, whether it be 0 or 1 is also 1. So I got 1 in both of these categories. Okay. Does these two dumb classifier at least the result does this statement make sense? Okay, so these two are again extremely dumb classifiers, right? But what they do is they achieve 2 points on this curve. Okay, so they achieve 2 points on this curve. So this curve is a classifier that always output 0, 0. There's a classifier that always outputs 0. There's a classifier that always outputs 1. Okay, on this curve. So you can achieve these 2 points. Then what happens if if you randomly flip a coin and pick whether the output 0 or 1, which the dumb classifier you use? What you can achieve is you can achieve every point between the line of these two things. Okay, every point in between the line can be achieved. This is 1, 1. This is 0, 0. Okay. So if your performance is gauged between a trade-off between false positive and true positive, this line you can always achieve. The way you achieve this is you basically flip a coin, see which of the dumb classifier you use, and pick that one. You can do no worse than this line. You do no worse in this line by using two very extremely dumb classifiers. Okay, right? So the two dumb classifier gets those 2 points. Now, how do you get the line? You just sort of randomly pick a probability of which classifier you're using. So you can get this line. You get this line. Okay, so this line is called the performance for a random classifier. Okay, if you have a random classifier that does sort of doesn't care what the input is, you get at least this line. Okay. So what does this mean is your algorithm, right? So you want to do better than this line because, right? So again, more towards this direction, the better the algorithm. You want false positive to be very small, true positive to be very large. So you're trying to go to this corner, okay? You can at least get to this 45-degree line by doing very dumb things. So your classifier should do better than this 45-degree line. I should go to this direction, okay? So this is a way of looking at how good a classifier is. This is sort of another way to report. Is how do you compare against something that's just randomly flipping coins at this line, okay? Right, so this is the comparison you want to make, right? You want to end up, close to this point. Right? You want to be here, okay? You'll be surprised how many classifiers end up in this range, especially once the problem gets complicated. There'll be complicated classifier you can train that end up here, which is worse than randomly flipping coins. Right? Yeah. Right. Yeah, so 0, 1 is the best, right? I have no false positive, good. I have all the true positive, which is also good. This I want to go to 0, 1, right? So anything above is good, better than random guess. Anything below is worse than random guess, which means your algorithm is useless at this point, right? If your algorithm ends up here, that's a useless algorithm. You cannot even beat a random guess. Okay, so you should at least be able to beat random guess using your algorithm. Okay. No, so you can basically look at your data and tune some parameter to see, if you control this rate, where does this rate go? But anyways, you can, by dividing your data into different amount, you can see sort of how this curve gets traded off. Right? So you can have some data, you can divide the data into a house or more positive, more negative, and look at how this curve is drawn in this case. No, so this includes 0, right? Because for false positive and true positive, so implicit include 0, right? These implicit include 0. Right? So because if you don't guess 1, then it's 0. So this is a binary. So getting 1 correct, meaning you're getting 0 correct. Right? So getting true positive correct means that you're getting the 1 correct. Getting false positive correct means you're getting 0 correct. Right? So again, this is only useful for binary. More other categories this doesn't work, but at least for binary, this is the picture you look at. Okay? So you have this this is called ROC curve. Right? So again, you want to be here, right? So most times your algorithm, looks something like this. So this is sort of good algorithm. Right, so this is good performance, right? So you're doing a lot better than random guessing. Okay, so you plot this is an example of performance, then you're sort of very much closer to the 1, 0, 1 point than this random guess. Okay, so this is the idea of plotting this curve. Be away, do much better than just doing random things. Okay. All right, and the way you measure how much better is you basically looking at the area under the curve. So what you want is you want a large area under this red curve. Right? So the larger the area under the curve, the better it is, because the largest area you can get is 1. Right? So you have a perfect classifier, the area under this is 1. So for your classifier that's good, the area under the curve should be close to 1. Okay, so we're not going to sort of do too much of this calculation, but this is another sort of popular way of showing how good your classifier is. Okay, so the classifier, there's many things you can show. Normally you show this curve, ROC curve. You look at precision, recall, F-score, accuracy, and so on. So again, it is very, very dangerous to take one, just one of those scores and optimize it. Okay, you may risky, doing something worse than random or something like this. Okay. All right, so we'll stop here today. And next class, we'll pick up from here and look at something more complicated. For example, what if you have more than two outputs? If you have sort of m number of outputs, how do you deal with that? We'll look at more sophisticated method. We'll look at support vector machines. And then we'll look at the neural networks, which is a generalization of all these things.